Hello and welcome to Chapter 8 of MECH 3331 Fluid Mechanics. In this chapter, we'll look at viscous flow in pipes. Specifically, I'll be covering these sections from the book, section 8.1 to 8.6, that cover the characteristics, laminar pipe flow, turbulent pipe flow, pipe losses, and a few examples, as well as pipe flow rate measurement in section 8.6. Now, pipe flow is quite common. It's part of most mechanical devices. Fluid is always transported from one subsystem to another, or you are also used to common examples like pipe flow network, transporting drinking water, or oil and gas pipelines, or it could be blood flow within your body, or it could be in process industries where chemicals are transported. These are, of course, not the only type of pipe flows, but in general, we are used to seeing them. If we think of characteristics of pipe flow, the most prominent characteristic is it laminar or turbulent flow? What is laminar and what is turbulent? Laminar means in nice, steady, uniform layers of fluid without significant bulk mixing and time dependent effects. That is, if you have a flow and you monitor the velocity at any particular point, and if we have a velocity measurement at that point, the velocity at A as a function of time is nearly constant and has no real fluctuations. This would be a laminar flow, an example of a laminar flow. Turbulent flow on the example is punctuated by rapid fluctuations in the velocity at that point and the oscillation about a mean. So turbulent flow is the opposite of laminar. It has rapid fluctuations and unsteady effects. The word turbulent itself is common from everyday life experience. Turbulent means something that's not to be trusted or it's unexpected. And in between the laminar and turbulent flow, we have what is called as transition, which is mostly steady except periods of unsteadiness, or it could be intermittency, and these would be transitional. Okay. If you have a flow, if you have a flow coming in, if this were laminar, and let's say you inject a small amount of dye in one of the layers, over time the dye will diffuse slowly to other layers, and this dye layer might be only diffusing a little bit. So the diffusion is dominated by slow propagation amongst the molecules. That is a characteristic of laminar flow. If on the other hand, if the same dye is injected in a turbulent flow, you have these rapid mixing, liquid layers being swirled around in all directions. Okay, and what will happen is this dye slowly is quickly dissipated across the entire cross section, leading to rapid mixing due to movement of fluid masses by vortices or swirls or little tornadoes. Okay, that would be a characteristic of turbulent flow. The other characteristic of pipe flow is that of uh, entrance region and fully developed region. Now what do I mean by that? Let's say if I have a pipe, I have flow entering the pipe. Okay. Now if you have viscous flow past a surface, we can say that the fluid that is very near to the surface is decelerated by the surface. In fact, the surface and the flow are at the same velocity, and this is called the no slip condition. The fluid, I'll say it a little bit differently. The relative velocity between the fluid and solid surface is 0, meaning the fluid is also at rest because the wall is not moving, so it's also at rest. Okay, the fluid that is near the wall or that is very next to the wall is at a velocity 0 on either side. Okay, I have a pipe flow. Okay, so I have uniform flow coming in. The fluid that is attached to this wall is at rest. It pulls back the fluid layer that is to the very next layer, and and as a result, the fluid layer here slows down a little bit. This layer pulls on the next layer a little bit also, and progressively the drag exerted by the wall is felt through the entire cross section. So what will happen is the fluid that is very next to the wall is brought to 0. It pulls back a little on the fluid that is next to the wall, which pulls back a little bit on the fluid that is a little bit further away, and so on, and until the center line you get what is the classic parabolic shape velocity profile. Okay, and the development of this parabolic velocity profile takes a certain distance. That is, here the fluid enters with uniform velocity, and a certain length down the line, let's call it L, the fluid velocity becomes fully parabolic. This is the L is the distance where it becomes fully parabolic. L is the distance for the velocity profile to become fully parabolic. We call it fully developed flow from here on. Fully developed flow from here on. So any flow whose velocity profile is fully viscous, any I'll say internal flow or pipe flow whose velocity profile is fully viscous is called fully developed flow, and the distance it takes to become fully developed is called the developing length. The developing length. Okay. Next, we proceed on to the analysis of fully developed laminar flow. Fully developed laminar pipe flow. Okay, and we begin by first of all considering a circular pipe. Okay, we have a circular pipe of radius r, and we have a fully developed flow, which means the flow profile is fully viscous. Okay, we have a flow profile that is fully viscous. Okay, and we are trying to understand first of all what is the velocity profile u as a function of r, and what is the expression for flow rate as its relation stands with respect with the pressure drop, the radius, the length of the pipe, and the viscosity of the fluid. You want to determine this relationship. We make some assumptions in the analysis. The first assumption being we have a steady flow, okay, and we have an incompressible flow in which density is a constant. We have a Newtonian fluid, that is the relation between shear stress and velocity gradient is linearly related, and mu is the dynamic viscosity. Okay, so we are going to do this by considering a flow element. So here is the pipe flow, here is the axis. Okay, I'm going to consider a flow element whose radius, or a cylindrical element whose radius is r and whose length is L. Okay, here is a cylinder whose radius is r and length is L. Okay, on the left face of the cylinder, I'm going to say a pressure of P1 acts on the left face. Okay, P1. Okay, a little bit down the line, I'm going to say a pressure P1 minus delta P P1 minus delta P acts on the right face. Okay, and on the curved face, I have a shear stress tau acting on the surface. Okay, shear stress tau. Okay, this is also in figure 8.8 of the book. Okay, so at steady state, because I have steady flow, I can assume that there is a steady state. I apply a force balance on this cylindrical element. What is my force balance? Sum of all the forces acting on the left face or acting to the left must balance sum of all the forces that act on the right. Okay, so by that I can write P1 times pi r squared minus P1 minus delta P times pi r squared minus tau times 2 pi rl equals 0. 2 pi rl being the curved surface area of the cylinder and pi r squared being the cross section area. Okay, I can simplify all this, and that's going to give me delta P divided by L equals 2 tau divided by R. okay, or I have delta P. Delta P is the pressure drop, over the length L of the element. Okay, so if I rearrange this, I have tau equals delta P over L times R over 2. Okay, now if I set R equals uppercase R, the radius of the cylindrical pipe, I have R being a variable and this surface is R equals R. When the radius equals when R equals the radius, we have tau equals the wall shear stress. Tau W is the shear stress at the wall. Okay, is the shear stress at the wall. Okay, so I'm going to write tau W equals delta P over L times R over 2. Okay, so what do I have? I have tau equals delta P divided by L times R over 2, and wall shear stress equals delta P over L times uppercase R over 2. Tau W can be measured, and that's why we identify it as a separate property. So I can take the ratio of these two numbers. I can write tau equals tau W times R divided by capital R. Okay, which I can use in the first relation to write delta P over L times R over 2 equals tau W times R over R, or delta P over L equals 4 times tau W over D, is 2 times tau W over R, or delta P equals 2 L times tau W over R, which is 4L times tau W over D, where D is the diameter, since it is common to specify diameter than radii of pipes. Okay. One of the conditions that we assume in this analysis is that of Newtonian flow or Newtonian fluid, which obeys the law tau equals mu du dy. If you want to have a picture, here is tau, here is the velocity profile. Okay, this is u, this direction is y, and what we have as du by dy is the velocity gradient, the variation of u along y. That's the velocity gradient, and that's related to the shear stress in terms of the dynamic viscosity. Okay, that is, you can think of it as tau changes in the direction, tau changes along the direction in which u changes. Okay, in the notation associated with pipe flow, we write tau equals minus u du by dr. Okay, minus u du by dr. Why do we include the minus sign? here is the pipe, here is the surface where u is 0, here is the surface where shear stress is maximum, and here is the surface where you are going to see u is going to be maximum, and here is the surface where shear stress is going to be 0. That is, in the direction in which u increases, in the direction in which u increases, okay, tau actually decreases. So tau goes from maximum to 0. Okay, so this negative sign means tau increases when u, when u, which also decreases, which also increases with r, decreases. Tau is positive when du by dr is negative, and tau is negative when du by dr is positive. Okay, so we are going to write tau equals minus mu du over dr. Okay, we also wrote that tau equals delta p divided by L times r over 2. We can combine these two equations and write mu du by dr equals minus delta p by L times r over 2. Okay, or I can write this compactly. Du by dr is minus delta p 2 mu L times r. Okay, I'm going to of course repeat this in the next page. Du by dr is minus delta p divided by 2 mu L over r. So recall this problem. We have our cylindrical element whose radius is r. The radius of the pipe that we are interested in analyzing is r equals 0 to r equals r. If we first want to solve for velocity profile, we would want to integrate du from the wall at which u is 0 to any radial location u of r. This would be wall which is r equals r to any location r, and I have the other side minus delta p 2 mu L r dr from r to r. Okay, so this is u of r minus 0 equals minus delta p by 2 mu L times r squared over 2 integrated from any value of r, or from uppercase r to any value of r. So I have u of r equals minus delta p divided by 2 mu L r squared minus r squared divided by 2. So I have u of r equals minus delta p by 4 mu L times r squared minus r squared. I'm going to write this slightly differently. This is delta p 4 mu L times r squared 1 minus r squared over r squared. Okay, that is u of r. Okay, and radius is related to the diameter as d over 2. So I can write this as u of r is delta p over 16 mu L times d squared times 1 minus 2r over d the whole squared. That would be the velocity profile. So that is the velocity profile. U of r is written in terms of delta p times d squared divided by 16 mu L times 1 minus 2r by d the whole square. Okay, we'll call this quantity here as Vc, the center line velocity. The center line velocity, because if you set r equals 0, you get this quantity as your u, which is the center line velocity. So if you have a pipe flow, the quantity delta P by L is simply the pressure drop across your pipe. So across this section, the pressure drop is delta P and the length is L. Delta P by L is called the pressure gradient. Delta P by L is the pressure gradient, so we'll treat it like one quantity, and d is the diameter, of course, and mu is the viscosity of the fluid. So I have the center line velocity to be delta P by L times d squared over 16 mu. Okay. Now the next thing of interest is for us to calculate the volumetric flow rate, which you would calculate as U of R times the area element integrated from r equals 0 to r equals r, and the area element is 2 pi r dr. Okay, so if you plug that in, Q is 0 to r, I have Vc times 1 minus r over r squared times 2 pi r dr. So I have 2 pi Vc times 0 to r minus r cube over r squared dr. This would be 2 pi Vc r squared over 2 minus r to the 4th over 4 times divided by r squared. So I have pi over 2 Vc times r squared, or this is 1/2 the center line velocity times the area of cross section. Okay, so if I put the numbers in, I have Q equals pi by 128 mu times delta P over L, delta P over L times d to the 4th. This is a pure number times viscosity. This is viscosity. This is the pressure gradient, and this is the diameter of the pipe. Important proportionalities that you should remember. Q is proportional to delta P divided by L. Q is also proportional to the diameter to the 4th. This is really important. Why is it important? It means the flow rate is very sensitive to the diameter. You double the diameter, if you go from D to 2D, you're going from Q to 16Q. Okay, you are making the flow rate 16 times. If you are doubling the pressure gradient, you are merely doubling the flow rate. And Q is also inversely proportional to viscosity. Okay, so important to remember, Q is proportional to d power 4.